Erwin and Matt today. Let's give them a big DEF CON welcome.
Okay, good morning all. Thanks for being here early, for some of you who don't have kids yet. So, just a quick introduction. So, I'm Erwin, that's Matthijs or Matt, if you may want to call him. We both work at Nixu, which is a Finnish company, but we actually work for the Dutch branch office. So, we're based in Amsterdam. And as you can see, it took us quite some time to get here. What is it what we're going to talk about? Well, we're going to talk about wireless industrial sensor networks, but it's always good to look back at what has been done before. As you can see, the earliest research was already done in 2009, more academic research about potential attacks. And the attacks were described but not demonstrated. There was no information how you could actually recreate the attack yourself. And that sort of continues, because then in 2015 there was actually a PhD student in the Netherlands who did also similar research and actually tried to build a tool to interact with these networks, and he didn't really succeed. So he was using SDR-based systems initially. In the end, he didn't really succeed in actually capturing traffic or modifying traffic. So then we came along and we did a presentation at S4. And then we already opted the idea to actually create a toolkit to be able to actually capture traffic, inject traffic, etc. That's a couple of years ago, but unfortunately we never got around to actually doing it, because we soon left the company we were working at that time. And in the meantime, we had Blake Johnson again using an SDR-based approach to interact with these networks, but again, no code was released, no tools, nothing. So, I mean, these networks are around for quite a while, but still there are no tools. And we strongly believe in Wright's principle, which is written down there. The guy, Joshua Wright, who actually said that, well, if there are no tools, security will not improve. So, we were actually attending DEF CON last year as just, and not as a speaker, but as a regular visitor, and we're like, well, let's build those tools, because it's still missing. And just to give you an idea what the industrial revolution is for these type of systems. So first, we're talking about industrial control systems here. So first we had the air pressure systems in 1940s. In 1950s, they started using analog current loops. In the meantime, I'm well familiar with that part, because it actually allowed me to destroy some of the components we were testing. But later on, they actually started creating digital protocols. So on top of the current loop, they implemented, for instance, the HART protocol, which you may be familiar with or not. And in the late 2000s, they thought, well, let's do it wireless. And they created two standards, wireless HART and ISA 111A, commonly named as ISA 100. So, is anybody familiar with these protocols? Have ever heard about it? No? No, not that many. Okay. Well, so it's for most people it's very niche, but still it's interesting. And if you're wondering where these systems are being used, for instance, oil and gas fields, you can see those transmitters. So you see the blue ones. They're actually field devices. So those are transmitters, and they're actually measuring things like pressure or temperature. And they transmit wirelessly to the central system. But we get to that. Well, since it's an industrial control loop, process control loop, I think it's good to sort of explain how that works. So basically, you have a flow transmitter all the way on the right, and there's a signal being sent to a central controller, and that, for instance, indicates the flow rate. That's called the process value, and that process value is actually checked against a set point, and if it's within range, nothing happens, but if something needs to happen, there's actually control output, so that's the bottom line, and then the valve is actually changed from opened or closed to adjust the flow. So this is the typical process loop. And what you see is that typically, up till now, mainly the measuring part is done wireless, either with wireless HART or ISO 100. So if you look a bit more at wireless HART, it's actually the same HART protocol, the application layer, but they created a wireless stack for it. So it's compatible with the HART devices out there. It does use encryption, so it's not the most insecure control protocol. But it's symmetric encryption, and we get to that in the later slides a bit more. It's based on wireless technology from DOS networks, because they are also the ones creating the radios, so the radio system on the chip. And you see there's a couple of vendors who actually build equipment for wireless HART. So ISO 100, there are fewer companies actually supporting it. The main driver is Yokogawa and also Honeywell. And there's actually a whole bunch of standards it's based on. So there's 6 low WPAN, there's IPv6 surprisingly, and UDP on the top of that. And it allows you to tunnel under other protocols. So it's not like they took an existing protocol as with wireless HART and built a wireless stack for it, but you're able to tunnel. And so it's more vendor neutral. And mainly it's developed by a company called Nivis, who created the system on the chip initially. But now there are more chips out there from different vendors. So what does a typical topology look like? Well, these are mesh networks. So there is a central system that orchestrates the mesh. That's the gateway, network manager / security manager. Typically that's just one box, one device, as you can see on the right. But there are field devices out there, and there's a couple of different ones you can see in the picture. So you have the field devices that actually measure stuff. That have a wireless transmitter themselves, or you have the situation where, for instance, where you have a HART-enabled transmitter, and then you can add an adapter and they can communicate. But since it's a wireless mesh network, also the field devices can route traffic for other devices, so it's not point-to-point only. And you have, on the right-hand side, you have the wireless HART handheld, and that's being used to actually configure the devices. So before they can join the network, you have to configure them, and then they will join the network. So if we look at the protocol stacks, you can see that on the HART side, there's actually on the left-hand side, you can actually see the traditional HART, and on the right-hand side you see the wireless HART. So it's based on 802.15.4, but they used only a very thin layer of that protocol. But everything they build on top is specifically wireless HART. And one of the things to pay attention to is the channel hopping, because we get back to that later. That's something that was challenging to solve. And also on the ISO 100 side, we see a similar thing. So it's again a thin 802.15.4 layer, and then you see the whole protocol stack on top with UDP, etc., etc. And although it's not listed in this overview, they also do channel hopping as well. So to summarize the similarities, because we have 2 wireless protocols out there which are somewhat similar, and we thought, well, can we build a toolkit to actually assess both of those systems? So they both have they share the 802.15.4 layer, although they both have a different version, subversion, and they both work at 2.4 gigahertz. And they both do time-slotted channel hopping, and the reason they do that, so they hop from channel all the time, and the reason they do that is actually to minimize interference, because these systems are being used in plants, in industrial sites, so there is a lot of interference from other systems that are out there. And also to mitigate multipath fading. So that means that if a signal gets reflected back, you might cancel out the signal, and because you hop the channels, you actually prevent that. Because there's a lot of metal around, large storage containers, etc. So there's a lot of reflections. So they both have a central network and security manager to orchestrate the communication between the nodes. It doesn't mean that the nodes itself can also route traffic for other nodes, but there is a central point that controls the network. So we thought, well, we can probably build a sniffer for both protocols. So if we look a bit more at the things they share, is that they actually use this exact same ES CCM star encryption. So at the network layer, they use it for integrity only. So 802.15.4 is only integrity, but at the transport layer, they apply encryption. And both systems have actually a joint process where they actually share the encryption key. And that's a handshake with the network manager. So that's the central component. And for wireless HART, it's only shared secrets. So that's already an interesting thing. That it's symmetric encryption. So how do you get the key across, and where do you store it? And ISA 100 also supports certificates, although we haven't seen it being used. So the ISA 100 supports both shared secrets and certificates. And there's a lot of different keys. So if we started at the left, you have the ISA 100. The top three keys are actually used during the provisioning phase. So you have the global key, the key open, key global. And during the provisioning phase, the master key is being shared, and from that master key, they derive two keys: the D key and the T key. It's not so important that you remember all the different keys. It's just to show there's a lot of different keys out there. And the same is true for wireless HART. So the well-known key is used at the network layer. That's actually not an encryption key, but an authentication key, because they don't do encryption at the network layer. And there's a network key, then the join key for the join, which is being shared during the join process, and derived from that there's two session keys, so both for broadcast and unicast. So first question, of course, is how do you get key material? Well, one of the things you could do is actually read documentation, because there's a lot of default keys out there. And I must admit that since we've done the research 2 years ago, a lot of the documentation is not publicly available anymore, because we back then already published some of the keys that are default keys. And it seems a lot of the documents have vanished. So not all the keys we list here you can still publicly find. But we're pretty sure that we initially found them somewhere. And ISA 100 specifically also has over-the-air provisioning of devices, so that's also a weak part where you could sniff the transaction or the handshake. But then you need to be able to sniff, of course. And previous research we've done, we actually took apart transmitters and looked at if we could interface directly with the radio sock, because actually there's multiple components and there is a radio sock on there. And it turned out that they actually had JTAG SPI enabled, at least for wireless HART, because back then we only looked at wireless HART. And we showed that you could actually sort of locate where the encryption key is. And worst case, you can always dump the complete firmware and load it onto another similar device, and then you can also join the network. So there's a couple of ways to actually obtain those keys. So if you are a plant manager and you're getting rid of old equipment, also pay attention to the last one, because you might not erase those keys, and if it ends up on eBay, somebody might buy it. So there's a couple of default keys for wireless HART. We haven't located any default keys for ISA 100 yet, so that's why we only list wireless HART keys. The first one you see a lot, and that actually has to do with Dust Networks, who create the socks, and that's why they use Dust Networks ROC at a lot of locations. So you can see it's a 16 bytes hexadecimal key, so it's quite long. But you can see they use a couple of values out there. And the third one, the Emerson one, is also interesting because that's taken from an Emerson wireless hard gateway. And if you do a factory reset, it actually sets the key like this. So you see a lot of zeros. So the key space is really, really small. So if you ever have reset those devices and use the default key, you might be able to easily brute force it. And sometimes you can see it's also the name of the vendor. So the last one is actually exactly Andres and Hauser, button hacks. So if we look at the sniffer hardware, we first looked what's out there because we want to build something new. And during previous research, we used the Beam Logic, which basically is just a sniffer, but it sniffs on all 16 channels simultaneously. So it has no injection support, a very basic Wireshark dissector, and it's quite expensive. It's the box on the right. So yeah, it's expensive and also quite limited what you can do with it. Initially we thought about using the Atmel RC Raven stick, because also the regular transmitters use an AVR based system. But already reached end of life, and it's very hard nowadays to find Admin Studio somewhere. So then we looked for other options, and we went on to the B-Kit from NXP. And by default that already allows you to sniff on one channel. With the standard firmware, although the standard firmware is not open source, but that also reached end of life. So we continued our search for another stick from NXP. So this one is still supported, has a free IDE, and it allows you to sniff on a single channel. It's quite powerful, and we need that for the channel hopping, that Matthijs will explain later. And you can actually modify the PCB a bit to put an external antenna on it. It's extremely small, so I already ruined the device trying to do it. But it is possible, and you could go drawer driving. Yeah, there's documentation out there and examples, but only with a few important omissions here and there. So I just want to show you the default application that's already provided by them. I hope you can see it. So basically this is the default application. You just select the channel, so it's sniffing 802.15.4. You can start Wireshark, and you can at least see packets. See, you can see the packets, but if you click on actually on the bottom side, you can see that it's just data, so it doesn't have a dissector for this protocol. But the basis is there. We can already sniff packets on one channel, so that's a start. So then we figured out, okay, how does this actually work? Because there's a whole SDK around it, but actually it's relatively simple because the hardware is detected as a virtual COM port, both on Windows and Linux, so that's already a plus. But they implemented their own protocol, which is called FSCI. It's developed by NXP, and it's a communication protocol over serial. And there's a host SDK available with Python bindings. But we thought, well, we don't want to ship a tool with the whole host SDK around it. We might run into legal issues, so can we communicate directly? And as it turns out, we can actually do that. So we created a driver for Killer Bee, and Killer Bee can directly drive this stick now. So we don't need a full SDK anymore. So this is what it looks like schematically. So the KW41Z is actually the M Cortex. There's a second one on there where you can actually load different bootloaders, and that way you can also provision new firmware on the device through USB. So you actually have the MCU Expresso, it's called. MCU Expresso IDE, and actually allows you to develop firmware for this device. So, up to you.
Thank you, Aaron. So we wanted to build something more powerful than was out there. So we thought we found our hardware platform that we could develop on. So we start building the tool set, and the first thing we wanted to accomplish is well, sniff the packets ourselves and not relying on the SDK that came along with the hardware. So actually we built a driver for the Killer Bee framework. Killer Bee because it shares the same RF layer, the 802.15.4 protocol. So that seems quite a good match. And we also developed extensions to Scapy, so we were also able to inject packets rather than just listening on the traffic. And to bring packet sniffing to the masses, we also decided to build Wireshark detectors for protocols Wireless Heart and ISI 100. So we'll show you a short demo. It's in action. So you can see we use the ZB Wireshark utility that comes with Killer Bee. And here you see we are picking up traffic, in this case ISA 100, and you see also the Wireshark detector in action. On the left of the screen you see we decode the packets. So the next challenge was the channel hopping problem. So like Aaron told, the protocol uses a fast-paced channel hopping algorithm. And when starting developing and studying this toolkit, we thought, okay, there's a new extension for 802.15.4. If I remember correctly, that's the D amendment, which also uses time hopping mechanism. So we thought, well, maybe we could use that because that primitive was already supported by the SDK. But it turned out that that was not usable at all. So we really got to get our hands dirty and write, a pretty extension to the firmware itself. So none of us having an embedded development background, that turns out to be quite a challenge. So if I mean fast-paced channel hopping, that means that the intervals you see here on the slide are at 10 milliseconds. So every 10 milliseconds you get the frequency change. So yeah, in order to keep up, you have to think through how you're going to accomplish that. As I said, we need to rely on the firmware itself, on the hardware, because yes, you can change channels from the host system, but as soon as you send an FSCI command to the USB device, the time slot already has lapsed, so that doesn't work in practice. So you really need to implement this in firmware. So we needed to deep dive into embedded development, which was new for us. There are a couple of approaches you can take. So for this type of devices, you can rely on a real-time operating system. There are quite a few around. One of them is FreeRTOS, for instance. But it is pretty. It's pretty complex in the sense that it's not a full-fledged operating system, but it has a task scheduler that will preempt So that means that it will interrupt your code right in the middle of your function, and you can get all kinds of challenges, like race conditions you have to deal with. So you need to mess around with semaphores and other synchronization mechanisms. The other approach is use a bare metal task scheduler. That will not interrupt right into your code section, but as soon as the task is scheduled and is running your code, you're responsible for releasing the resources. So that means that in practice you have to make sure that your code doesn't run for longer than 2 milliseconds. Otherwise, you will starve other tasks, and that means that, for instance, there's a separate task for collecting the packets. You can make sure that you change channels, but if you don't pick up the packets, you don't have anything at all. So, as I said, it requires quite some discipline and in programming. The upside is that you can achieve fast execution because you don't have the overhead of a real-time operating system. So this is what it looks like. These are the modules in the firmware. A part is offered by the framework itself, so you have a memory management task that is taking care of allocating the heap and stuff. You have the MAC-PHY layer that's taking care of picking up the packets from the radio. And the serial manager, obviously, because these packets need to go to the host. You have a bunch of timers that you can program and will wake your task, so you can do actually something useful with these packets. And of course, everybody needs blinky lights. So on the right side, you see actually what we needed to do. The MAC-PHY layer was only partially useful. We needed to implement the channel hopping, and that is called the MAC extension layer, because we needed to obviously extend these capabilities. On top of that, we actually get to the industrial protocols, ISA 100 and wireless HART. And we also needed to parse information out of these packets on that layer, because we needed the information in order to calculate when a particular time slot occurs where you're interested in. So how to do this? 10 milliseconds. If you program a timer to wake up your task every 10 milliseconds, we found out that you're always too late, because you're never guaranteed to get a wake-up call within every 10 milliseconds. It's either 10 milliseconds or 11 or 12. And when you start tuning into the channel, you're too late. So what we did is we parsed the packets that came along. So in the advertisements of both wireless protocols, you get information where the slots of interest are. For example, the join slots. These are the time slots where field devices actually can tune in to start a handshake for getting onto the network. Those are of particular interest, also from a tech perspective. So what we started to do is, tune in advance. So if our tuning code gets called, we measure, okay, the next slot of interest is 3 time slots away. Okay, we'll tune in right now. And, the other task will take care of picking up the packets there. So that gives us some more room, like for instance, around 40 milliseconds rather than 10 milliseconds. So that turned out to work pretty well. And we'll show you how we actually achieve channel hopping. Again, ZB Wireshark. We had to hack in a non-existing channel. Channel 0 means that we activate the channel hopping in the firmware. And as you can see, we get quite some more traffic here than in the first case, where we only were tuned into one particular channel. And I don't know if it's readable, but here you can see that on the left part that we actually hop to different channels. So, what can you do if you can tune on these intervals of interest, these time slots? Well, these are a few attacks that have been theorized, and now we can execute in practice. One is just jam the signal on by sending garbage on a particular channel, and you can block, for example, advertisements. And if you do that successfully, no new devices can join the network because they are not able to synchronize with the network. Or even existing field devices will lose at some point the synchronization with the network. So in practice that means that the field devices are unable to send their process values, and depending on what control system you have, you can wreak havoc. Of course, being able to inject traffic, you can also transmit fake advertisements. So you can entice field devices to join your network rather than the existing network. And we'll give a short demonstration of how you can jam. No? Yeah, okay. So here you see the victim who's happily receiving advertisements. And we turn to the attacker, which will start our tool to jam the signal. We found the network, and on the victim side you see a few packets coming in, and next it comes to a halt. Silence. So that's all nice, that we can do things without actually being on the network. But suppose you have gathered some keys, or you found these in the manuals, or you brute force these. Well, you can do all other nasty stuff. The way this works is that the encryption actually is derived from a nonce that has, for a large part, predictable values. So there's in the advertisement data there is a counter that you need, and that can be snipped from the network without being authenticated. But even if you don't know how to you can mess with this nonce value, because there is a replay. Thank you. there is a replay protection in place. That's supposed to protect against, obviously, replaying fake values. But the thing is, if you mess with the nonce, and you'll guess a valid nonce, and it will be picked up by the device. If it's larger, it's much larger than the timestamp that is currently in the network, it will reject all packets from valid devices. So you can really bring down an entire sensor network this way. Of course, if you also have access to other key material, for example, when capturing a join process, and you have access to the session keys, you are free to mimic a real field device, and you can really mess with process values. And that's where it's getting really scary. So, to summarize, what did we learn along the road? These sensor protocols are a highly unexplored area, and as in the introduction, we suspect that this is mainly due to the fact that no real good tools exist. So yeah, we picked up that task and hope that we can promote other researchers to explore this very interesting area. So yeah, we intend to release the tool set we created, and yeah, another thing we want to give to the asset owners who deploy these systems. We see a trend that people are getting very confident with this technology because it's around for 10 years and it has never been hacked, so must be secure, right? So you see a trend that these protocols are not only being used for monitoring systems, but also for control. Yeah, I would like to well, probably that's not a really good idea, so they might want to reconsider that. All right, we have some time for questions, 5 minutes I see, so these are the future research areas, these are the topics we want to expand upon, so we'll support more attacks that have been theorized so far, but no tooling exists. We want to create support for war driving industrial networks. When we ordered the hardware, we were happy to see that it had an external antenna connector, but once it arrived, it was not on the board, so we were kind of disappointed. And of course, with the capability of actually interacting with this network and the capability of injecting packets, yeah, we are free to actually fuzz these protocols from the radio side of these systems. Okay, well, thank you for your attention, and we can take some questions now.